Hello everyone, today's 5 questions. First question is based on lens maker's formula, and the question is the radius of curvature of the curved surface of a plano convex lens is 20 centimeter, and if the refractive index of the material of the lens is 1.5, then how does it behave for an object which is lying towards a concave side, convex side, or towards a plane side? So out of these four options we have to check. So first option is it acts as a convex lens only for the object which is lying towards the curved side. It acts as a concave lens for the object that lies on the curved side, or it acts as a convex lens irrespective of the side on which the object lies. And D option is act as a concave lens irrespective of side on which the object lies. So out of these four options we have to check the correct option. So here plano convex lens. Here how to draw the plano convex lens? You see here the first word is plano, so you have to draw it like this. This is a plane surface and this is the convex surface. So this type of lens is a plano convex. Suppose if the object is lying this side towards the plane side, this would be the incident ray, this is a principal axis, and here this surface would be the surface number 1. So R1 for the plane surface would be infinity, and R2 would be for the second surface, and the R2 for this surface would be towards this side, so you are going opposite to the incident ray, so it has to be negative 20 centimeter. Now using the lens maker's formula, this is mu, and mu is also given as 1.5. It is mu minus 1 over R1 minus 1 by R2. So when you will substitute all these values, 1.5 minus 1 over R1 is infinity, minus 1 by 20. So this minus would become positive, and this would become 0, 1 over infinity. 1.5 minus 1 would become 0.5 into 1 over 20, or this can be written as 5 over 200, so 40. So it means, taking the reciprocal, f is equal to 40 centimeter. So here f is positive. Now if the object is lying towards a curved surface, here again I am drawing the plano convex lens, and if the object is lying here this side, this would be the incident ray, and this would be the surface number 1, the surface on which the ray is getting incident first, that is the surface number 1, and this would be the surface number 2. So you see here R1 is in this direction, and it is going in the direction of the incident ray, so R1 would be positive 20 centimeter, and here R2 would be infinity, which is the plane surface. Mu would be same. So in this case, if you're finding f, it would be mu minus 1 over R1 minus 1 by R2. So this is 1.5 minus 1. R1 is what? This is 1 over 20, and infinity, R2 is infinity. So substituting all the values, this would become 0.5 into 1 by 20. So again the same thing we are going to get, we are getting, that is 5 over 200. So f is again plus 40 centimeter. So here option number C is correct, that it acts as a convex lens. Here also it is 40 in the first case, also we got 40 only, which is positive. So when the focal length is positive, in that case we say that the this lens behaves as a converging lens, or it acts as a convex lens irrespective of the side on which the object lies. So whether the object is lying towards a plane side or towards a curved side, the behavior is same, that is it behaves as a convex lens. So option C is correct for first question. Next question is question number 2. It's given as the equiconvex lens. Equiconvex lens here is the lens convex lens which is having the same radii of curvature for both of the surfaces. Here this convex lens is having a focal length of 15 centimeter, and it is cut into 2 equal halves in thickness. What is the focal length of each half? So here we are having a equiconvex lens, and its focal length is given as 15, as this is convex lens, yes, 15 centimeter, so it would be positive focal length. Now, in thickness, it is being divided into two equal halves, and we have to find out the focal length of each half. So first case, when it is not cut. So what was the focal length? 1 over f is equal to mu minus 1 over r1 minus 1 over r2. Now this is equiconvex lens. So if the object is lying this side, so this is surface number 1. So r1 is r and r2 is minus r. So if you will substitute these values, 1 over f is equal to mu minus 1, r1 is r and r2 is minus r. So here this would become positive, and 1 over f would be mu minus 1 2 by r. So this is the expression of the focal length when it was not cut. Now, as we are going to cut the convex lens into two equal halves, so one half is this, another half is this. Now let us see what is the focal length. If the object is lying this side, so this is the surface number 1. Here r1 is r and r2 is infinity. Now let us find out the focal length. So new focal length would be f dash, mu is same, mu minus 1 over r1. r1 is r and r2 is infinity. Now you see this would become 1 over f dash is equal to mu minus 1 over r. So you can see the difference between the two. 1 over f was mu minus 1. Here also we have mu minus 1. This is 2 by r and this is 1 by r. So you see this focal length is 2 by r. So if you want to make the comparison, you can take the ratio of the two, 1 over f over 1 over f dash. So this is mu minus 1 2 by r, and here it is mu minus 1 by r. This get cancelled, this is cancelled, and this would become f dash over f dash over f. So this is 2, or we can say f dash would become 2 times f. Here it appears that it is 2 times, but no, this is 1 over f. So here we have to find out the proper value of f. How this focal length is going to get changed. So you have to take the reciprocal here also and here also, or you can simply take the ratio of the two equations to find out the focal length. So new focal length would become double the initial focal length. Initial focal length was given as 15 centimeter, as f was 15 centimeters. So new focal length would become 2 into 15, that is 30 centimeters. So focal length of the lens would get increased if we are cutting the lens into two equal halves. Next question number 3 is a beam of light converges at point P. Now the convex lens is placed in the path of the convergent beam at 15 centimeter from P. At what point does the beam converge if the convex lens has a focal length 10 centimeter? Okay, so here already some beam is getting converged. Question number 3 we are going to start. A beam is already converging at some point. Let us consider it is converging at point P. Here, let this beam is already getting converged at point P, and now what we are doing, we are placing one convex lens at a distance 15 centimeter from point P in the path of the convergent beam. Now let us consider we are going to place one convex lens here at a distance 15 centimeter from point P. And the focal length of the lens is also given as 10 centimeter. And we have to find out the new position of the convergent point. At what point does the beam converge? Now we need to find out the new position where the beam is going to get converged. Now as convex lens is converging lens, so already the beam which is converging at point P, this lens would converge it more. So it means the point is going to get shifted towards the lens somewhere here. Now we have to find out the exact position using the lens equation. So here you see focal length we have, this is plus 10 centimeter, and we need to find out, because I need to find out the final position here of the image. So this lens is going to give me the image of this point P. Now this point P would be behaving as you see, these are the incident ray on the lens. So we can say that these rays are coming from the object, because these are the incident rays on the lens. But as these rays are coming from some point and they're going to converge at point P, so point P can be considered here as a virtual object for the lens. So object distance would be plus 15 centimeters. So this is a special case where u is positive. Otherwise, for all real objects, u is always negative. But you see here, P is being the virtual object, and when you're going to find out the distance of this object, you have to go in the direction of the incident ray. So using sign conventions, this u would be positive 15, and f is, because the lens is convex lens, so it is plus 10 centimeter, and we need to find out v. So using the lens equation, I can find 1 over f is equal to 1 over v minus 1 by u, and 1 over v can be written as 1 over f plus 1 by u. 1 over f is given as 1 by 10, u is 1 by 15 plus 15, and this can be written as 33 plus 2. Okay, so 1 over v would be 5 over 30. 5 6 are 30, and v is 6 centimeter. So this is the new position of the point where the ray is going to get converged. So somewhere here from lens, it is at 6 centimeter the ray would get converged. So this was the question number 3. Now let us solve question number 4. Fourth question is, a spherical convex surface, here it's not lens, it is surface, a spherical convex surface of radius of curvature 20 centimeter made of glass of refractive index 1.5 is placed in air. Find the position of the image formed if the point object is placed at 30 centimeter from the convex surface on the principal axis. So question number 4 is a numerical based on refraction through spherical surface. So here we are having a spherical surface, and this is our denser medium, and the refractive index of this denser medium is 1.5, and the radius of curvature is also given as 20 centimeter. R is given as 20 centimeter. So I'm writing here. R is 20 centimeter, mu is 1.5, and the position of the object is 30 centimeter in front of the convex surface. So u here is minus 30 centimeter. So means here object is placed on the principal axis. Object is placed here. This is the incident ray. Here we are having normal. This is the center of curvature, and instead of going forward, the ray would bend towards a normal, and we would get image somewhere here. So this position of image we have to find out, and we have to use a direct formula here. Direct formula here is, if this is mu1, and mu1 here is as this is placed in air. So this is mu air, which is 1. So using the formula, mu1, that is mu air over minus u plus mu over v is equal to mu2 minus mu1, that is mu2 here is the mu of the higher refractive index minus mu air over r. So this formula we have to use, Mu air is 1, so this can be written as 1 over minus u, that is minus 30, plus mu is 1.5 over v. We have to calculate. Mu minus mu a, 1.5 minus 1 over r is given as 20 centimeter. So this distance is 20 centimeter. This would be positive because it is taken in the direction of the incident ray. This is 20 centimeter. Now solving this, it is 1 over 30 plus 1.5 over v is equal to 0.5 over 20. So from here we have to find out the value of v. So little simplification, 1.5 over v is equal to 5 over 200. I'm just removing the point from here, and this would go to this side. This would become 1 over 30. So the LCM would be 600 and 315 minus 20. So here this is 1.5 over v is equal to 15 minus 20 is minus 5. 1.5 into 600 over minus 5. This would be the value of v. 0.3. 6 3s are 18. 180. So this is the value of v. Here v is negative, so it means the image is being formed in the air, not inside the thick material or optically denser medium. So here v has to be in this medium, this side. So it means it is not that much converging, so that we are getting the image here. So convergence may be lesser and it may be extending in the backward direction to give us the virtual image in the air. So here image is formed at 180 centimeter from convex surface in the air. Okay, so this was your question number 4. Question number 5 here is, calculate the radius of curvature of an equiconcave lens of refractive index 1.5. Lens is having refractive index 1.5 and this is the refractive index of the lens, and it is placed in medium of refractive index 1.4, and the lens is equiconcave lens and its power is given as -5 diopter. So we can write what's the focal length. Focal length is, as we know that power is what this is, 1 over f, if f you want in meter, and 100 over f when f is in centimeter. So f in centimeter can be written as 100 over power. So we can write f centimeter may 1, and this is 100 over -5 diopter, that is -20 centimeter. So this is the focal length of the lens. This is -20 centimeter. Now using the lens maker's formula for equiconcave lens, we know that for equiconcave lens it is 1 over r1 minus 1 over r2, and you will substitute equal values using sign conventions. Here you get -2 by r. So little simplification, this is 1 over minus 20 is equal to 1.5, 1.4 minus 1 minus 2 over r. This we have to find out. Minus 1 over 20, 1.5 minus 1.4 over 1.4 into minus 2 by r. This minus minus get cancelled. So 1 over 20 is equal to 0.1 over 1.4 into 2 by r. So this would become 0.7. This minus this point get cancelled. So what we are left with, we have now 1 over 20 is equal to 1 over 7r. I'm taking r this side and 20 this side. So r is 20 by 7 in centimeter, or r can be written as 2.14685 approx centimeter. So this would be the radius of curvature for the two surfaces of biconcave lens. Thank you.